Okay, in this video, let's do some examples of finding derivatives, and we're going to think of them as functions. So I'm gonna write down a function. I'm gonna write down, say, f of x equals the square root of 11. Let's say theta. So let's not have x, but let's have theta. Okay, and we want to find f prime of let's say 1, f prime at 10, let's say f prime at 10/11. So if maybe I'm trying to find this at a bunch of different spots, and I know that I'm going to be wanting to take the derivative at a bunch of different spots, and I don't want to take that limit 3 or 4 times. Okay, so we're going to take it with a variable in there, and then we're going to evaluate the derivative at that variable. And so we're going to calculate the limit as h goes to 0. And it's not going to be x, but it's going to be theta plus h. So it's going to be the square root of 11 times theta plus h minus the square root of 11 theta over h, right? So I've plugged in the variable plus a little bit into the first one, just the variable into the second one, and divided by that difference. And now we need to evaluate this. So we evaluate this by using a difference of squares, right? I'm going to multiply top and bottom by that conjugate bit, and I'm going to get rid of the square roots. So this is going to be 11 times theta plus h minus 11 theta, all divided by h times the square root of 11 theta plus h plus the square root of 11 theta, right? We're going to see what happens as h goes to 0. Well, this all simplifies. The 11 theta and the 11 theta are going to cancel. On the top, I'm going to have just an h, which is going to cancel with the h on the bottom. So this is going to be the limit as h goes to 0 of 1 over the square root of 11 times theta plus h plus the square root of 11 theta, which is, oh sorry, I have an 11 on top. There we go. If I plug in h equals 0, nothing bad happens, so I can just plug it in. There's no division by 0 or anything we have to worry about. So this is going to be 11, and then I'm going to have 2 square roots of 11 on the denominator, right? So this is the square root of 11 with a theta down there over 2 square roots of 11 theta. Nope, sorry, that's not true. I don't need the 11 down there because I canceled it. I just need the square root of theta down there. There we go. The square root of 11 on the denominator cancels with half of that factor of 11 in the numerator, and I end up with this. Okay, so if I wanted to evaluate this at 1, f prime at 1 is the square root of 11 over 2 square roots of 1, which is the square root of 11 over 2. F prime at, say, 10, that's the square root of 11 over 2 square roots of 10. F prime at, say, 10 over 11, that's the square root of 11 over 2 over the square root of 10 over 11, which is the square root of 11 multiplied to each other, so I get 11 over 2 square roots of 10. And so I don't actually have to take the limit each of these times to evaluate these. I can just plug in after I've taken the derivative arbitrarily at a variable theta. I can plug that theta value in for whatever I want it to be. Okay, so there's that one. Let's see another one where I use that alternative definition of the derivative. Let's look at, say, let's say f of x is equal to, well, let's do it with just something kind of simple, x squared. and we're going to take the limit as y gets close to x of y squared minus x squared over y minus x. Okay, what happened before was everything was kind of simple because I usually could factor out just a h period. But now what you're going to be trying to find as a factor is going to be a y minus x in the numerator, right? And so what happens here is I get to use a difference of squares in this case. And I have that as a y minus x and a y plus x over a y minus x. And those guys cancel, so I no longer have 0 over 0 when I set y equal to x. I can set y equal to x because I'm getting y's that are closer and closer to x, and nothing bad happens when I set y equal to x, so now I end up with a 2x in this case. So the derivative of x squared is 2x. And like I said, with the h in the denominator, all you're looking for is a factor of h to cancel out. Now, if this is your form, you're going to be looking for a factor of y minus x in the numerator to cancel that out, to get rid of that 0 divided by 0 situation. Okay, let's look at one of these graphically. And here's the graph that we've got. I'm going to have something like this. Okay, and we're going to have a solid dot there. We'll have a point there that I know, and here's it. I've got 0, 0. Let's say this is at, let's say that's at 2, and this is at minus 1. Let's say that's at 1, and that's at 2. Okay, and maybe this guy's at, maybe that's the square root of 2. Okay. So at which points does this thing appear to be differentiable? Well, it appears to be differentiable everywhere except for this point and maybe the end points. This is left differentiable there. It looks like it's differentiable all of these points off to infinity, so it's probably differentiable at -1 up to 0, not at 0, so I'm going to union 0 off to infinity and say that it's differentiable all of those points. Okay, it's probably left differentiable at this, or sorry, right differentiable from the right at this point. If I'm moving in from above, from the right, it's looking like this thing has a smooth value there, but it's not fully differentiable there, so we just include the open interval, not including those endpoints. Okay. Where does this have a positive derivative? Where is the derivative positive? Well, where it's positive is where the slope is positive, right? So it would be an increasing function. And from 0 on to the right, it looks like it has a positive slope. It looks like it's increasing from 0 off to infinity. Okay. Where is it negative? Where's the graph decreasing? Well, like I said, we can't include that endpoint, so it's going to be decreasing from -1 up until 0. Okay. We can't include the endpoint because we don't know what it's doing at that endpoint. Maybe it's going off this way, but maybe it's going down that way. Maybe it's not even differentiable there. We don't know what happens to the left of that. And to have increase or decrease, you have to have a change around that point. If it's just the endpoint, we only have change in one direction. We can't say for sure what the other direction's doing. Maybe it's flat there, and that type of stuff. Okay, so that's kind of an idea of what happens with these types of things. I don't have any place for sure where the derivative is 0 in this. If I had a graph that had definitely a maximum there, it's no longer going up, it's no longer a positive slope, and then a negative slope, the slope going from positive to negative would sort of indicate that there's a zero slope here at that top. Or if I had a bottom, there'd be a minimum, there'd be a zero slope on that minimum. Okay, but that is something we're going to talk about extensively in the future with optimization type things. We'll be trying to find those maximums and those minimums. Okay, I think that's enough for this video. I will see you guys tomorrow, and good luck.